percent differences were fairly small, right? There was a couple around 7 or 8%, right? It's most of 1% or less. And if you plot those, like you notice there were only 4 concentrations of substrate we did instead of 5, like in the ethanol one, so it's fewer data points. If you plot those, like this group down here, so no pyrazole, these are the amounts of NAD. Now, how did I get this concentration? I added 50 microliters of NAD. The original NAD was 0.1 molar. That calculates to 5 millimolar. It's the same way you did the other one. It's 50 microliters times 0.1 molar equals 1,000 microliters times M2. And we're looking for M2. So it's 50 microliters times 0.1 molar divided by 1,000 microliters. We get 5 millimolar. Right? If you wanted in molar, it'd be 0.0. And we convert it to millimolar. That's what we want to report it in. Right? The average velocity still have units of per minute. We haven't changed anything about that. I recorded them over the same times, so times 60 still results in per minute. Right? So if I plot these, do I get a hyperbolic plot? Looks hyperbolic to me. This point could be a little lower, right? But it looks pretty straight. So if I take the reciprocal of those, like this, and plot those, I should get a nice straight line. Looks pretty straight. Which point looks a little off in this graph? And I'll give you a hint. If I throw a trend line on there, it should
the one on top.
Yeah.
Oh.
So which one?
The last one.
The last one, not this one.
Yeah, the last one.
Right. This one's the problem.
Yep.
Right. If it were but a little higher or lower, it would be great.
Higher.
If it were a little higher, you see it would line up with the. So when you see trend lines like this, like you will on the exams, don't assume this point is the problem, because it's not. It's this one. Because if it were higher, it would line up perfectly with the other 3. And we already said on the previous graph I did, this one, where I took the slopes, so the averages versus the concentrations, that I said this point looked a little high. That one there should be a little lower, because it should make a nice hyperbolic curve. If this point were a little lower, that is the point on the other graph. Right? We make the other graph again. Right? That is this point on this graph. And if it's a little low on the first one, right? Sorry, a little high on the first one, it's a little low on this one. So this one should be a bit higher, and it would line up with the others. So let's see what the slope or the trend line gives me for that one. R squared looks not great. Right? 0.98 is not very straight. And it's always that last point, because it's the lowest substrate concentration. That's the problem. And if you go back and look at their data for that point, which is this point, right? The lowest concentration of NAD with no pyrazole, which was up here. That's these data, right? And you notice they agree fairly well, but it's a rather slow process. This doesn't change very much. Okay? So we're getting very slow, and it's going to get worse. Okay? If I plot the next set, do it the same way. You notice I'm not keeping any of these graphs. I'm just looking at them to see if it looks hyperbolic. So does this one look hyperbolic?
Yes.
Yeah, it's definitely reaching a maximum, right? And it's definitely slowing down as we get here. So this one I expect it to be a bit lower again, right? But it's not quite there. Right? And if I plot them the other way, reciprocals, that should get a straight line. And does any point look like it's not a long straight line? Trend line should help you see it.
Yeah. It's a little bit off.
Which one?
The last one?
The last one again, right? These three line up perfect, but the one out here, that one is again a bit low. If it were a little higher, which tells me again, like I said on the first one, it's a little too fast. Right? So, and then if we plot all three of those on the same graph, we get something like this. These are the exact same ones I just did, the 9, 8, 6. This was the one I just plotted. It was really close. And this one's really off, right? And that's the hard one to get because it's got all that inhibitor in there. So the numbers are hard to calculate correctly. The main reason is you're limited by the specs you have, right? Look at the velocities, or sorry, the absorbance changes for this last one. Very little substrate, but plenty of pyrazole. And look how much it changed. So every 5 seconds, you can literally watch the numbers tick by. So when they wrote down the measurement for the 15 seconds, too, right? That could make a huge difference at this point. Whereas back here, they were flying by. You notice how fast these were changing. Right? So it's much more accurate when it's going fast. But here, we're limited by, I don't know that next number. If I had 0.125 next number, it would be better. So I'm getting into the limits of my resolution. That's why they don't look so. But with these data, which pattern can you definitely eliminate from the possibilities?
It's not competitive.
They definitely don't cross on the axis. If they do cross, if they do cross at all, it's somewhere far to the left. Does that make sense to everybody? I can't say they're absolutely parallel yet, because they look parallel, but they definitely don't cross on the y-axis. I can eliminate that possibility. So it is not competitive. So I'm choosing between uncompetitive and what number should I go check to see that are they the same? Like go check the slope because I'm thinking these are parallel. So I got the slope of each of those lines right here, right? And it shows that they're about the same. They're not changing very much, right? What about the y-intercepts? Quite different, right? 1.3, 4.6, and 8, right? So they're quite different for the intercepts, which you can see those numbers right here on the, right? So which one of these patterns does it represent? Which is the best? Now these numbers aren't r-squareds of 1. So on the screen, take a look and which one is it best fit by?
Uncompetitive.
Uncompetitive. So that's what we call this an uncompetitive inhibition. So I actually wrote that here. Okay. And then for the previous one, we had a competitive inhibition pattern. Okay, so far? So from those two things, I need to describe a few things to you so you need more information for that because that's nice that we know those two things, but I don't know how to calculate anything yet. I haven't showed you how to. Okay, so let me bring up this PowerPoint. It's a really short version of the one I used. I think Kimberly told you the dog story. All right, did you tell this class too?
Yes.
Maybe she's not here.
I am here. Wait!
But I think she told you guys the dog story, right?
Yeah.
I'm here. I'm just doing the screen recording. Sorry.
Okay. So, you know the different types, competitive, uncompetitive. But let's do some math with types, right? So you guys have gone over all of this part. Competitive definitely has that intersecting pattern on the y-axis. Uncompetitive has the parallel lines pattern. And non-competitive intersects, but definitely to the left of the y-axis. Okay? And if you remind you, you can say this whole slide in 2 sentences, right? So looking on the right with the schemes, the ability to bind to free enzyme, which occurs in which of the types? Where can the inhibitor bind to free enzyme? Which of these 3 types?
Competitive.
Is that the only one?
Non-competitive.
Right. So competitive and non-competitive both have the ability, or both have the potential for the enzyme to bind, or sorry, the inhibitor to bind to free enzyme. In uncompetitive, it clearly doesn't do that, right?
Right.
So what do competitive and uncompetitive graphs have in common?
They both intercept at one point.
which tells you what? What's another way of saying that? Where they intersect was not what you said. That's excellent. But they do intersect. I agree. But what's another way of saying that? If lines intersect, they are not
parallel.
they're not parallel. And what's another way to say exactly that? If they're not parallel, they
don't have the same slope.
Exactly. They have different slopes. So, that's, all that was correct. Everything you said was correct. I'm just leading you to a conclusion.
Okay.
So clearly, the ability to bind to free enzyme affects or changes the
slope.
Exactly. Now do this other comparison for me. What do uncompetitive and non-competitive have in common? The second and the third. Not the graph, but the schemes on the right. What do uncompetitive and non-competitive have in common?
They both bind to ES.
They both can bind to ES, right? Where competitive definitely doesn't. Okay. So what do they have in common in the graph? That competitive most certainly does not.
Different y-intercepts.
They have a changing or a different y-intercept. So restate the same sentence. The ability to bind to ES changes the
y-intercept.
Y-intercept, exactly. So let's put those two sentences together, the two we just said. The ability to bind to free enzyme changes the slope, and the ability to bind to ES changes the intercept, y-intercept. That's the two sentences I'm referring to. And we can say those two in a corollary as well. So let me state them again, and then I'll give you the ability to bind to free enzyme changes the slope. The ability to bind to ES changes the y-intercept. The inability, in other words, you can't bind to free enzyme, does not change the slope. That would give me a parallel line, right? And the inability to bind to ES does not change the intercept. That would give me the same intercept. Right? So those two statements and their corollary say the same. And it gives you the three patterns. So what can you tell me about your enzyme in lab, alcohol dehydrogenase? Just from what you know so far, what can you tell me? Which type of inhibition did we see?
Competitive
Is that the only type we saw?
and uncompetitive.
How can we see both?
It bind it to both ES and E.
If it bound to both, it would be non-competitive. We definitely didn't see that. It's something else. You got to think a little differently than what's on the screen. I know this is not an easy question. Look back at your Excel sheet. What did you do in this experiment?
Then we changed the ethanol.
You varied the ethanol, right, in the presence or absence of the inhibitor. And what did you do in the next one?
Varied NAD.
Right. So what are we talking about when we say E and S and ES? The S thing.
Free enzyme is substrate.
Right, but what is the S here in our experiment? We have two substrates. We have ethanol and we have NAD, right? So we have to look at them independently. There's not just one substrate like those diagrams. When we're doing the varying of NAD, you notice you held the ethanol constant. You didn't change it at all. We just added the same amount every time. When we varied the ethanol, you guys did this. We held the NAD constant. We added 20 microliters of 0.1 molar every time. Okay, so we hold one constant and vary the other, and it gives you the effects of that substrate. But we have two substrates, right? So there's a couple possibilities here. I think I went over this with Wednesday. I don't know if I did it on Monday while we were there. But there's a couple possibilities. You guys remember? Have you guys gone over this in class? Maybe you have. Maybe I talked about it. I don't remember. But you could have substrates binding to enzyme in multiple ways. You could have either one bind first, or one must bind before the other. It could be ordered. Right? Did we go over that type of stuff
Yes, I went over that.
with both sections?
Yes.
Okay. I probably wasn't listening when you were doing it, which you didn't want me to do anyway.
This is
But-
true.
So you went over the silly analogy.
Drug deal on a bus? I mean, cookie deal on a bus?
Yeah, the cookie deal on the bus.
Yes, I did.
Okay, so you guys understand the difference in that? The three types there? So number one, we could have everybody on the enzyme pile on, everybody on the bus, do the reaction, and then everybody get off the bus. Right? All the enzymes leave, all the products leave, all the products leave the enzyme. That's random. Everybody gets on, sits in whatever seat you want, and then it happens, and then everybody gets on, right? So that's a random event, right? But everybody had to be on the enzyme. All the substrates had to be there for it to happen. So it's called sequential, right? And if everybody has to be there, it's called sequential. If everybody has to be there and everybody has assigned seats, like you have to get on first because you have a window seat, and then you have to get on next because you have an aisle seat. In the case of an enzyme, one substrate binds definitely first, and then the other one binds. That's called ordered sequential because there's an order to getting on the bus or getting on the enzyme, right? If it's random who gets on first and it doesn't make, it's just called random sequential, right? And then the other type is the non-sequential ones. It's called double displacement, which means one substrate gets on the enzyme, performs some chemistry, and part of itself leaves. Maybe it leaves a methyl group behind, OH group behind. Maybe it leaves half the protein behind, half the enzyme, or half the molecule behind. Whatever it might be, there's something happens and it leaves with a part of itself behind. The enzyme has been modified. Then the second substrate shows up, picks up that leftover piece, and leaves with it. Right? That was the letters that you guys saw where, say, Q shows up, binds the enzyme, and then O leaves, leaving the little tail behind. And then substrate P shows up, grabs a little tail, and leaves as all. That's why I like to use those letters. Right? That's called double displacement, and the key there is the two substrates never see each other. They're never on the enzyme at the same time. It's simply two half reactions. Everybody following that? Right? In all these scenarios, we have multiple, right? And at least two. And that's the case we have with alcohol dehydrogenase. There are two substrates, ethanol and NAD. I'd like to know which of those three patterns this enzyme does. Right? And from what we have here, we can figure that out. So I'm going to bring up a drawing program so you can see what I'm doing, but help you maybe see the difference in the three. So you can have double displacement, or you can have sequential, and under sequential is it random ordered? That's what we have to decide. And we have all the information we need for it, and I'll show you how to do it. Right, so I'm going to bring up this program so you guys can watch what I'm doing. And hopefully this not so terrible, probably will be terrible drawing. So we'll start out with, we'll draw a line, right? And I'm going to need some characters here. All right, can you guys see those?
Yeah.
Okay. I know you can't see my mouse, but you can see when I'm highlighting stuff, right?
Yes.
Okay. Maybe these are too small. Make it bigger. That might help. Okay, so in the first one, I just drew a line. We start with just a free enzyme, and we must end with a free enzyme. These are Cleveland diagrams. Okay, I think you guys have seen these, right? And so in our scenario of let's say random sequential, what would happen in that case? Well, ethanol could bind first, right? We could say ethanol could bind first, then NAD can get on, right?
Right.
Like I'm drawing on the whiteboard, it's just not so fast. All right, so an NAD could bind next. And at that point, we have an E-ethanol complex and then an E-ethanol NAD. Then in this region here, right, can you guys see the box I'm making?
Yes.
In this region here, some chemistry takes place, and then our products leave, right? So we have something like the two products leave, right? Whatever they are, the NADH and the acetaldehyde. We don't really care about that side, right? That's one possibility. The other possibility is what? These two bind like this. NAD first, then ethanol, right? So if it's random which one binds first, I have to modify my drawing a little bit. So I'm going to draw it this way. Let's move these out of here real quick. So this could take two paths at this point. They're not very straight lines, I apologize. Looks terrible. Right. That looks very bad. But you could have NAD bind here, then ethanol, or you could have ethanol bind first, and then NAD. That terrible looking graph makes some sort of sense?
Yeah.
Right? I can follow that path, right? So I can either NAD binds first, then ethanol, then I do it. Or I could have ethanol bind first, then NAD, then this happens in the products. And so this little graph here represents what I'm highlighting, right? The random binding, the random sequential. Okay? This one up here represents what? Where NAD must bind before ethanol. That's what this is saying. There's no other path here.
Ordered.
Ordered sequential. So that's ordered sequential. So let me put this one up here at the top. We'll call that one the random one.
Make sure to talk about this in your lab report, guys.
Yeah.
Whatever one you
So-
determine.
Here's a random sequential one, right? I gotta separate these by some lines. Right? And then here's another ordered sequential down here, but I need to switch the order. Because there's two possibilities for the order, right? Ethanol first or NAD. Right? So here's three options that we're going to look at. Right? And we're not really worried about which products we're leaving. So we're only concerned with the left side of these graphs. And so in the first scenario, we have either substrate could bind first. Let me get a marker here. So in the first scenario, we have either substrate could bind first, NAD or ethanol, then the other, but we arrive at a common goal here. Okay? And then, of course, they leave in various random orders. Or NAD definitely binds before ethanol, but they end up both here again, and then they leave in a specific order. Or the other order, ethanol first, then NAD, then they end up together and leave. Right? So these are the three sequential possibilities. One random one and two ordered one. The other possibility, which I haven't drawn on the screen, is double displacement. So let me scroll down and add that one for you. So, draw this one more time. In that scenario, we have ethanol binding perhaps, and then something leaves, right? And then NAD comes along and binds, and then something else leaves. Maybe ethanol left an OH group behind, right? And the rest of it left. And NAD comes along and picks it up, right? That's a possibility, right? So we'll leave that one on the screen as another possibility. And we'll see which one it is. Okay, so let's look back at our data. Do we have any? Which one of these is possible? Well, if you look back at the ethanol data, perhaps, right? So varying ethanol with respect to the inhibitor, we found out it was what type of inhibition. That's all we really need to figure this out. What type of inhibition is this?
Competitive.
What does that mean? What does competitive mean? There's no math in what we're doing. It's all logic.
Means once one binds, the other cannot.
Once what binds?
Substrate or the inhibitor.
Right, so once substrate binds, the inhibitor cannot, or if inhibitor binds, the substrate cannot. Which means the inhibitor binds when with respect to the substrate? Before. It can't bind after, right? That's because it lost. That's the idea here. So this tells me the inhibitor, pyrazole, binds before or after ethanol.
This one is after.
No.
Wait, the pyrazole or the
Pyrazole is the inhibitor, right? So ethanol varying it, and I get a competitive pattern versus pyrazole, tells me pyrazole must bind in the presence or absence of ethanol.
absence?
Absence. So it must bind before or after ethanol does?
Before.
Before. Because if ethanol's there, it's lost. Does that make sense? If ethanol's already bound, pyrazole can't bind. That's what this graph tells me, because it's truly competitive. Okay, so the inhibitor pyrazole must bind before ethanol. Looking at our graphs here, I'll do it in red. Right? What region, right, on this graph represents before ethanol binds? I'm just going to do it with like a brush. We'll shade it. Right? What region here represents before ethanol? That's any time up to here. Does that make sense?
Right.
And on this one, following this path, it's any time before here, because ethanol binds at these points. On this one, that's any time up through there. And on this one, any time before ethanol binds, like that. Okay, we'll just talk about those first. We'll only deal with this guy if the first three don't work. Okay. Everybody understand why I drew the lines to where they went? So anywhere up to this point, or this point, and on this one, anywhere up to here. On this one, as long as ethanol is not bound. Is this little shading making sense for everybody?
Yeah.
Okay. All right. So all that work to get this graph ends up as this information here. Okay. Let's move on to the other graph that you did with the data I gave you. Right. This pattern is what?
Changing the NAD. Parallel.
For the varying NAD, yes.
Parallel.
The parallel, which tells me what type of pattern.
Uncompetitive.
Not competitive.
Exactly. Now remind me again, what is uncompetitive? The substrate and the inhibitor, when and where can it bind? Well, not necessarily where, but when can it bind?
The ES complex.
It can bind to only the ES complex, right? No other scenario. So that tells me that the pyrazole here, it's the same inhibitor, can only bind how with respect to NAD? When we say ES complex, in this case, S is referring to the thing we're varying. So pyrazole can only bind to the ENAD complex. What does that mean about the timing?
So after the addition of NAD.
only after NAD. So if we go back to, where's only after NAD in this graph? Well, here, right? You can find anywhere in that area. Anywhere in this area, right?
Yeah.
Or here. After NAD is found, right? So that's on the first one. And the second one here, that's only after NAD, right? So that's this area. So far, so good. And then the third one, only here. Everybody agree with those? Only after NAD is bound, right? So are these two statements we just said, the pyrazole can only bind before ethanol, and it can only bind after NAD has bound. Are they both simultaneously true? We are doing the same reaction in both experiments, right? This is the same pyrazole molecule. It's the exact same reaction. So both of those statements must be true simultaneously. So it must bind after NAD, but before ethanol. One of these scenarios makes sense. The other two do not. Right, so let's look at the one that's easy to figure out. Look at the third scenario. Is there any point on this timeline, right here, any point on that timeline where blue and red occur simultaneously?
No.
So in this scenario, what I'm saying is ethanol, then NAD binds, right? That's what our scenario says. Is there any scenario, any possibility in there where NAD is bound, but ethanol is not? No, because we said it binds in the other order, that example. So the overlaps don't happen. So this is entirely not possible. All right, so this one is completely not true. Can't happen. There's no overlap between red and blue. Right? These have overlaps. Right? So this one here, entirely possible that NAD could be on the enzyme and the ethanol could not be, and that allows pyrazole to bind. Right?
Mm-hmm.
And what about the top one? Is that possible?
Maybe.
Well, the top one only gives
one option is
one option, right? So this whole thing, the top one, this whole part right here, hinges on the fact that both options must be possible for it to be random. If both options had appeared possible, then both of these as well. Right? If both of these work, then you knew it was random. But the top one, this area right here, doesn't work. It's not possible to follow that path. That means this whole thing is wrong. Right? Because you got to follow both paths for this whole thing to be possible. So that tells me this is what's happening. Right? So knowing these two inhibition patterns, and knowing what types and when things can bind, what do you know about this enzyme now? Just from doing a little bit of work.
it's ordered.
It's ordered sequential addition, and what's the order?
NAD first, then ethanol.
NAD must bind before ethanol. And there is no way for you to see the enzyme to know that, right? You can't look in the QPET and see which thing bound to the enzyme first. You have no way of seeing that visually. But from doing these inhibition experiments, we can figure that out. This is much like the dog figuring out what dancing is when not, and never seeing someone dance. Right? He doesn't understand it. But in the end, he can figure out what dancing is. Right? So we can't see the enzymes, but using the inhibition data, we can figure how they bind to the enzyme. It is ordered, and it's this order.
So I have a question. How would it look like if it was non-competitive?
So let's redraw one of these real quick. Get rid of some of this stuff. Okay. If it were non-competitive versus which?
Versus uncompetitive.
No, non-competitive versus which substrate?
Oh, ethanol.
Okay, just pick one. So how would we fill out this chart if it were non-competitive versus ethanol? What does that mean? Non-competitive means you could bind when
you can bind either or.
Right. So where on this line should I versus ethanol? Before it and after. Right? And same thing for the scenario down here. So far, so good?
Yeah.
What about the next one?
It's also before and after.
Yeah, it's pretty much the whole thing, right?
Mm-hmm.
And then what if you got non-competitive as well for NAD? What would it look like up here?
Also the same.
Before or after? Before or after? And in this one? Same thing. And same thing. So they all overlap everywhere, right? And since both of these are true, and they're mutually exclusive to each other, neither is true. That's how you get this one.
Okay.
So if they're both non-competitive, it's non-competitive versus trade, it means it was a random ordered of addition.
Yep.
Good question.
Thank you.
Okay. So we haven't dealt with this guy down here, right? So because we found an answer, double displacement down. And the only time you will ever have that is if you can't find an answer to the top three. So let's say we had something like we had competitive inhibition versus ethanol, like we did before, but we showed no inhibition whatsoever against it. No matter how much you add, right, it never changes. In other words, all your lines would not change. It'd be the same line all three times. So competitive versus ethanol means what? Let's draw that one up here. You can only bind when it's competitive versus ethanol. Competitive means you can only bind
Before. So
before the substrate bind. So up to here and up to there. Right? We can't bind anything else. And on this one
before, I don't know.
and before. Right? And on the last one, it would mean here as well. Right? But if I said no inhibition versus NAD, then it has no effect whatsoever. Okay? So I can't draw any blue lines on here. But what we can say is in this first scenario, this first one up here, like this, I have to get another rule across to you. Think about this for a second. We have an enzyme with two substrates. If the first substrate is put on, will anything happen? If it's in the first three scenarios here?
No.
No, I have to have everybody on the bus, right? But what if I put the second substrate on? Will the reaction take place?
Yes.
Yes. So if I put the first substrate on, nothing happens. I put in these first three scenarios. And I put the second substrate on, whatever one it might, the reaction will take off. Does the inhibitor have any chance of stopping it once the second substrate is on? No.
No.
So the inhibitor cannot bind anywhere past the second substrate. So can't bind past there, can't bind past here, or past here. Right? It's like a barrier. Once the second substrate is on, the inhibitor has lost the battle. You cannot stop this. So in each of these scenarios, is there any spot where you see that the inhibitor could bind?
The second option.
This one, right?
Oh, yeah, third. Sorry.
Right, the third one there, right? Because there's no place it can bind in the first one. There's no place in the second one. But the third one, there's an area, right? Right, well, let me change that to color. There's this area right here where it could bind between ethanol. Agree?
Yes.
If the inhibitor did bind there, would it show any effect versus NAD? It would mean it has to bind before NAD, correct?
Correct.
And that would mean it would be competitive versus NAD as well. But it would also have to bind after ethanol. And that would be uncompetitive versus ethanol. We didn't see those. We saw no inhibition whatsoever, which eliminates all of these options. Right? None of those can work. Right? That leaves me with this option down here. Right? So what it's telling me is The inhibitor binds right here. It binds after, oh, sorry, not right there. It binds right here. Before ethanol can bind, so it's competitive. But NAD's presence never occurs until the first half of the life. NAD's never there. That's why we're not seeing any inhibition versus. That's the only time you'll see that type of double displacement. It'll have some type of inhibition versus one, usually competitive, and no inhibition versus the other. Right? It's because I ran out of options in my first three. So anyway, after those options, knowing what you know about these, competitive versus ethanol, uncompetitive versus NAD, we definitely have an ordered sequential addition with which one binding first?
NAD.
NAD must bind first, followed by ethanol. And in the normal reaction, there's no pyrazole around. Inhibitor we added. So we used it to glean some information about the reaction. Not involved in the reaction. Right? All right, the last thing I want you to do is calculate some numbers. And this part I'm going to have to write an equation for you. That's going to be painful. So let me do that. So you guys remember the Michaelis-Menten, which says what? Velocity is you guys remember this, right? No one? I'm sure you did this in lecture.
Is it Vmax times substrate?
Times substrate concentration divided by
Km plus the substrate.
Right, sorry about that. I just sneezed and the cat clawed my leg. So it wasn't fun. So Km times S, or sorry, Vmax times S over Km plus. And we'll add a little divider in here. Right, so there's your Michaelis-Menten equation. Okay, I'm going to modify it a little bit. I think I showed you guys this modification where I multiply something times Vmax and something times Km.
The 1/1 plus the concentration of bitter over Ki.
Yes. So it's just a bigger equation. That's all. I'm just multiplying something here. So in parentheses here, I should have, it's going to be hard to type it, but something like this. I wrote this down for you guys, right? on the, I think we did it on the whiteboard last time. All right, maybe I can find a copy of it, but just write it out. Hey, you guys remember me writing that?
Yep.
Yeah.
Okay, actually, I think I have them upside down.
That's how you gave it to us in the lecture.
Yeah, so I'm gonna have to make some room here. That's multiplied times Vmax, and that's multiplied Km. And there's a big divider. It's ugly, I know, but you guys get the idea? I'm trying to draw this in paint. Okay, so keeping that in mind, let's put that on the side for now. And looking back at our information, how did I do with my PowerPoint? Oh, I know where it is. Okay, so looking at these things on the right, you told me competitive only binds to free enzyme, right? Like this graph on the right shows, this thing over here. And uncompetitive only binds to ES, and non-competitive could bind to either. So in the case of competitive, I think I got one over the lab. The KIS represents the dissociation constant of EI, how rapidly EI falls apart. And KII represents how fast ESI falls apart into ES and I. Right? So for competitive, it never binds to ES. The way of saying that is KII is infinity. Right? KIS is some real number. It never binds to ES. So if I had an arrow over there, the rate forming ESI would be 0. The rate on the up arrow is infinity. It never makes it. It falls apart infinitely well. I think we had that discussion last time we were in lab. Okay, so for a competitive inhibitor, KII is infinity. So if we go back to our information, we do here, we had a competitive inhibitor versus. Okay, so if we go back to my equations I just drew, in this case, KII is infinity. What happens to the thing in parentheses up here? What does this become? If KII is infinity, then I represents the inhibitor concentration, the I in brackets.
It's going to be
Divided
1.
by infinity means 0. And 1 plus 0 is 1. 1 over 1 is 1. So Vmax remains unchanged. Another way of writing that is this. Right, so the apparent Vmax, right, so this is the modified Vmax. The Vmax as it appears to the dog, right, or to us, what it appears to be is simply the regular Vmax times this. Right? I'm just pulling things out of that equation. So the apparent Vmax is the normal V times this thing in parentheses. Right? And we know that KII for a competitive inhibitor is infinite, correct? Which means these two things are equal to each other because the thing in parentheses reduces to 1. What's another way this is saying that the apparent Vmax is equal to, what does that say?
No change.
There's no change in the Vmax, which means there's no change in the y, because it's 1 over the Vmax. So if you go look at your intercepts, they were all the same. This is the true Vmax right there, with no pyrazole present. But in the presence of pyrazole, it didn't change very much, right? This one's a little off because that, but effectively it didn't change. And the math shows that, because this reduces to 1, right? This whole thing becomes 1. However, the Km, right? This is all for competitive. So the Km apparent equals what? The regular Km times this thing. And all I did was pull that out of the equation above, because that's the modified Km. That's what the Km appears to do. Well, for competitive, this, you know, became 1. Okay, that simplified to just 1. And this denominator down here, this I over KII is still infinity for competitive, goes away, right? It's 0. Which means the denominator here is just 1. That means this whole fraction is not really a fraction, it's just this. If I get how I did that?
Yeah.
Right? So what does this say? KIS, for competitive, is some real number, right? It's a real value. It's a positive real number. So I concentration is also some positive real number. It's the amount of inhibitor. So both of those are positive real values. And if I divide them, I will get some other positive real number. And if I add 1 to that, that's shown right here. I'm adding 1 to 6, I get a number bigger than 1. That's all I know about that. Well, if I multiply Km times a number bigger than 1, what happens to it? What is Km apparent equal? If I multiply Km, what was that? So
It'll be a larger number.
right, it gets bigger, right? So let's go look at our data and see if that's true. So here's the Km for the one without. You have to remember Km was just slope over intercept. Right, so I just did equal slope over intercept to get the Km. Same thing here and here. But this one's 14.6 millimolar. This one's 98 millimolar, and this one's 100 millimolar. So it's definitely going up. This one's not so reliable, but it's definitely going up, which is what this says it should. Okay. But if you know the Km apparent, right, we said it was 98, and I know this one. We just said it was 14.6 millimolar, and I know how much inhibitor I add. Can I calculate KIS? I know everything else in this equation. I can calculate this KIS from our data. So I just need to solve this equation for KIS. And it's just algebra. You guys can do that. I'll divide both sides by Km. Got over here. This actually works better than a whiteboard for because I can move things around. Everybody with me so far on the algebra?
Yeah.
Right? So these parentheses become unnecessary. Maybe get rid of the 1. Right? And then I would subtract 1 from both sides, right? Minus 1.
Divide by I.
Oops. And then I can switch the KIS for this whole thing, right? Multiply both sides by KIS and then divide both sides by this. This is essentially a fraction, right? I can rewrite it as I over KIS, correct? Same thing. And I can just switch the denominator down here for everything on the side. write this so it looks a little better. Equals that. And I'm going to throw some parentheses on this to help you see it. Right, so all of this is in the denominator. Right, so don't you know these numbers? Km apparent, is that bigger or smaller than Km? For a competitive inhibitor. It better be bigger because by definition it got larger. So this fraction here is definitely larger than what?
Then 1.
Larger than 1. So if I subtract 1 from it, it won't be great. It'll be whatever it is. I don't know what it is. It might still be bigger. Who knows what it is? But it's not negative. This is also a positive number, whatever the I. If I divide these two, I will get a positive. Right? And that's what I did in the chart here. So let's scroll over real quick so you guys can see that. Right? I had to calculate the concentration of pure in micromolar. Pyrazole was only 10 millimolar to start with, and you added 10 microliters into a total volume of 1,000. If you do that math, M1V1 equals M2V2. You can be able to do that, and you get a final concentration for pyrazole in millimolar of 0.1. But convert 0.1 millimolar to micromolar, and I want it in micromolar. If you do it for the set we added 20, you'll get 200 micromolar. So I made that little list here. Those are my concentrations. So how did I calculate the KO? Or sorry, the KIS. So I use this equation right here.
So is that +1 not over the fraction, or it is?
Say it again.
In the initial equation, the +1s are over the fraction, right?
Yeah, this is 1 plus this ratio. Right, oh, like right here at the top, this is 1 plus this fraction.
And the same for the bottom.
Right. The 1 is outside the fraction. So if I were to rewrite this one, I understand what you're asking. If I rewrite this guy over here, I could rewrite it like this. Get rid of that. Make that fraction. And it looks like that. And same thing with the bottom. Right? It's not 1 plus I, that quantity divided by, it's I over KII divided first, and then add 1. Does that answer your question?
Yeah.
It's an order of operations. Okay, so keeping this equation in mind, this one, I'm going to plug in the numbers I have. So that's what I did in here in Excel here. So this little equation right here, I typed it in, and it says take the Q45, which is 100 in micromolar, and divide by, now I need some of these I could do it myself. H50 is this part right here. That's my Km apparent. It's the Km in the presence of pyrazole, green box. Can you guys see when I move over the box?
Yeah.
Okay, I know you can't see my mouse, but I'm trying to make it light up. Right? Divided by the Km, the absence of pyrazole, that's the purple box. Right? And then outside of that division, -1. Close outside parenthesis. And it calculates it for me. It gives me 17.46, and that's in micromolar. Can you guys see down here that whatever units I has, that's the units that KIS has, because this is a unitless quantity? The Km apparent and the Km have the same unit. All right, so I got 17.46 or so. I could do the same equation again because you did another amount of inhibitor using 200, and I get something like 34. That one's not as good looking as the other one. Okay, but I can calculate those, and I'll just take an average of those. Those don't look very good, but we'll take them. Okay. I want you to do the same analysis for uncompetitive, which was these data. Okay. So for uncompetitive, looking back over here, KII, well, it's a real number, right? But KIS is infinity because it doesn't bind there. So going back to your equation, the original, this one right here one more time, I'll throw it on this side. So this was for competitive, but over here we're going to be doing uncompetitive. Everybody see what I'm doing? This side competitive, this side uncompetitive. What's true over here now?
Vmax changes.
Right, but what do I know about uncompetitive as far as these KIs go?
KIS is infinity.
Right, the KIS is infinity. So what can I change about these equations? Well, only this part, right? It's the only part that gets altered. KIS is infinity. What is this ratio?
0.
So 1 plus that would be
1.
Right, so this whole thing simplifies to what? I'll write it again. I can just get rid of this part, right? Gone.
It's just Vmax over Km. It's just the original one.
No, not really. Don't forget, I am adding S
There's
to
a plus. Oh, okay.
So I can't cancel. Right? Don't forget, I can't do that because I'm adding. But I can take this equation, which I've simplified, and pull some things out of it like I did before. What would Vmax apparent be? Right? This one simplified to just 1, right? That was very case is equal to what? Not 1. Right? This. That does not go away. Understand what I did? Vmax apparent is the Vmax we see in the presence of the inhibitor. Vmax is the normal Vmax in the absence of the inhibitor. Constant. It's still multiplied times something that is dependent on how much enzyme was there, how much inhibitor. It doesn't go away this time. Right? What can you tell me about Km apparent? Let's do Km apparent. It equals what?
Km
Yes,
times.
I'm sure you can do the math faster than I can draw it. It's Km times
That fraction.
all of that. Agree? So I've used this to pull out 2 equations. Right? But what can you tell me about these two? Don't they look similar?
Yeah.
Aren't Vmax and Km multiplied times the same things? So what would this ratio be? Vmax divided by Km. Wouldn't that be the same as these two divided by? The ratio of Vmax to Km, or either way, would not change, right? Because this would be on both sides. Everybody see that? Well, what is the ratio of Km to Vmax? Isn't that the slope of the line? And so that shows you why a competitive has lines. The math shows that this ratio, one constant to another, doesn't change. It did change for competitive because this guy was always the same. Okay, so can you use this equation to calculate KII now? Same way we did KIS. Just do some rearranging. So you guys work on that part. See if we can do it together. By the time you do it on your paper, I'll graphic. I'm going to take these 2 equations. Solve this for KII. Would this be under here? Everybody with me so far?
Yeah.
I'm just trying to do it. I'm very slow at using this thing to do it. Okay. Now what?
Flip it.
Yeah, flip the equations over. So this one on top of that one. That equals that one over 1, which just goes away, right?
Yeah. And then -1.
Let's subtract 1, so let's move that here. Throw another minus sign in there. Again, this is represented by I over KII, right? That's what that means. Okay, everybody follow the math so far? It's just out. And then what do? I can
Put
exchange
the whole fraction under I.
this for all of that. Make it look a little better. Again, I'll throw some parentheses on there to help you. Maybe make these lines a little longer. Right. Everybody see the equation? It looks almost like, and if I did that with the same equation here, it'd look exactly like this one. It'd look exactly like that if I'd replace this with that. So I have two equations to get the KII. All right, back to your data. What happens to the Vmax? Does it go up or down in the presence of the inhibitor? Uncompetitive.
It goes down.
No, so that means Vmax or Vmax apparent is a larger number. Which one of these two is a larger number?
Apparent.
So you told me in the presence of the inhibitor, which one is a larger number?
Oh, Vmax.
The regular Vmax, because in the presence of the inhibitor, it's small, right? So that means that ratio,
Positive.
well, of course it's positive because they're both positive.
Bigger than 1.
But yeah, you're not wrong by saying positive, but it's a positive number greater than. And if I subtract 1, it's still a positive number.
Yeah.
Now that's all we needed. So the denominator here is the amount of inhibitor is, of course, a concentration of a positive number, so this will be a positive. Right? What happens to the Km in terms of uncompetitive?
It goes down.
It goes down. So the apparent Km is smaller than the regular Km. Again, this number positive greater than 1. If I subtract 1, it's still positive, and I get a positive. They should give me the same answer. Right? So if you take those, let me move them real quick so you guys can see that while I do the Excel sheet. So what she did, same thing here. We calculated the concentration of pyrazole. And I can do this 4 times. Do this calculation 4 using this equation once with a certain amount of an inhibitor, using that equation a second time with more inhibitor, and then twice here. So that's what I did. So I reached over here and said the pyrazole concentration, I, divided by over C. Right? I50, which is here, the amount without inhibitor, Vmax, or in this case Km, whichever one I'm using, right? Divided by the one with it present, minus 1. And I did that for both 100 and 200, and 100 and 200 for Vmax as well. And all four numbers should agree fairly well. They're not terribly far off. So I would take the average of all four of these and tell me that's your KII, which is 43.1 something. Right, and then for the ethanol one, again, I would average these two and give something like 26. Okay. Everybody see how to do those? So you can get your KIIs and KIS, and you should put those in your lab report. And be able to do what I just did here. It's not that difficult, just algebra. Everybody have questions on those? This is the last time we're going to see this.
What are we averaging? You said you were averaging 2 KI from which samples?
So for the one where we vary the ethanol, I get two measurements. The one with 100 and 200. That was using this equation down here. Because I did it in two amounts of inhibitor, I got two apparent. For the one where I'm doing the NAD, and I got four answers, because I had two ways to get it, and I used two amounts of inhibitor each time. So for the first one, I'm going to average these two numbers. It's only two I can get. And for the second one, I'm going to average all four. And so this one will give you something like 43. This one should give you something around 26. Well, I don't know. Yours might be different. But for this one, you're using the data I gave you. Yeah. It's also true that when you calculate it in one way, they tend to agree more with each other. The other also agree internally. But be able to do the math to get there using this starting equation right here. And I just pulled out pieces of it and rearranged this all. But I had to know something. For competitive, I knew that the KII was infinity. For uncompetitive, I knew KIS was infinity, and it helps me get there. If it's non-competitive, then I can't change anything about it. The KISs and KIs are both valid, and yeah, you can solve for one and then solve for the other. Right? And I'll show you an example of what that looks like. If I can find it. Maybe it's in your folder. I don't see it. I'll put an example of the lab report on D2L for you. Don't copy it. Don't use it exactly like they did it. You should write your own report. But I'll put an example up there to show you how to think and lay out what you want to say. I just can't find it right now. I know it's in here. All right, questions on that? Post the steps for the math that is needed for lab report. Yes, it's all in there. It looks like above, Mohammed posted, I guess that's the data from the first one, where you varied the ethanol.
That's from the last.
Oh, from the one I gave you.
No, that's the one we did like the last Monday we went there.
Okay, so that's the one with the ethanol.
Yeah.
Okay, excellent. So, and I gave you the one with the NAD there. You didn't get to do that.
Okay.
But so I'll did the ones with the pH profile before that. And you may have to share your data with each other to get a complete set. I don't know if you did yet or not.
I haven't done that yet on the Excel, but I have the data.
Okay, so if it's pulled together, we can throw that up here. But you all had to share each other's data together.
Okay.
All right. What else did I miss while I was typing all that? How are we going to turn in the notebook? Interesting question. Kimberly's going to answer that one. Okay, so we only have a few minutes left for lab time, and I don't think it's enough time to go through all the papers, but and my guess is you have not read them all. That would be a fairly guess. Where'd it go? Here. So the papers are right here. These 5. I think they're on D2L as well. I want you to read all of those before we have our next lab, and we'll discuss what you need to know from them for the final exam. Okay, so the way the final exam questions work is going to be one question from each paper, right? And if you were to present, for instance, photosystem 2, right? I know you guys chose papers already. You had a note of a list of who was going to do what, and hopefully all 5 were covered. But whoever was supposed to do photosystem 2, not next week because it's spring break, right? But the following week, we're going to get in here and discuss it for probably an hour or so. We'll spend, like, I don't know, 10, 15 minutes on each one, something like that. And then we'll have that information for the final. But whoever was supposed to explain it to the rest of us in here, what that paper was about. You're not going to be graded on a presentation or anything. I want you to help explain it so everybody knows what they need to know for the final. And whatever you explain is what I'm going to ask them. And you should all have the papers so we don't have to share your like I'm doing. If you want to, I'll share mine. But we can pull up the paper and everybody look at it. For instance, if you're doing photosystem 2, all right, we'll all have the paper pulled up, and if you say, figure 1, we'll all scroll down to figure 1 and look at it while you're talking, right? So that's how I want you to do the presentations. Not really presentations, but lead the discussion, right? Talk about whatever you want to talk about, right? I don't want you to do the whole paper. We'll go through it. You're not going to be graded on it at all for participation. Help the rest of the class learn the material.
So there's no set thing that we should talk about for the papers, just whatever we think is important.
Whatever you want to. Whatever you find interesting. Put it that way, because if it's not interesting, you're probably not talking. So whatever you find interesting in the paper, tell us about it. But make it relevant. Don't tell me, that they wrote it on date. That's all I found in. That's not going to cut it. But find something interesting. Look at the figures, if nothing else, and try to explain 1 or 2 of the figures. Of course, you should read the papers, but then when we're discussing it, it'll make it a whole lot easier to read it ahead of time. That's why I'm not going to do it right now, because I know you have.
On the pH data, there are some values to the right that aren't in columns. Are those just repeating values?
I don't know what pH data we're looking at.
The one you posted on D2L, the pH Excel file.
Did Kimberly put that on there? I don't know if I don't think I did that. That must be her. Is this pH rate profile Monday?
Yes, if you download it, there are values off to the right.
I have no idea. Let me see.
The 3 values go.
Let me download it. Take a look. These here?
Yeah.
Don't know what those mean. It looks like this was a full set of data, so repeating their information here. And that looks like another copy of this. Maybe it was just a third group did pH perhaps? Or, I see. Some groups only had 1. Some pHs were done twice, and they don't agree very well. These 2 do not agree.
So what do we do with that data?
So this is where your graph comes. Use that, the average and the pH. This is, so don't worry about these at all. Just this. And that should be what generated this graph. Yes. So ignore all these numbers over here. Just use these numbers I've highlighted to generate your graph. And your graph should look like this. It should not be a connect the dot thing. You don't know what happened to pH 8.5. It could have gone up higher and it'll be on the way back down. You also don't know what happened between any other two. You can't really draw a line. But from this graph, you should conclude that the optimum pH is in what range? What do you think? Based on this graph, the optimum pH is
8.5.
8.5 and 9.
not necessarily. It's definitely between 8 and 9. I don't know where the peak occurred. It could have been before, it could be on its way down either way, but it's definitely between 8 and 9. Does that make sense to everybody? I don't know exactly where it is, but it's definitely between 8 and 9. Right? So don't draw a conclusion that it is 8, but it's definitely between 8 and 9. We used 8.5 because that's the buffer I made, but the idea might be 8. Maybe 8.3. We have no idea, but it's between 8 and 9, definitely, based on these data. Right. Kimbo, do you have anything else you want to add before we finish? We'll do papers next time, crystallography next time. Like I said, the papers will only take about an hour, maybe an hour, like that. And then I'll go over the crystallography. It's a good hour and a half tutorial that you'll work with me. And it's perfect for this type of arrangement. And actually, I think it will work better here than it will in the lab, because I'll be sitting at the computer the whole time.
Also, on the reports, are we supposed to include calculations?
You include methods. I'm going to put an example report up. Follow. Don't necessarily copy their stuff, but follow their pattern, follow their layout.
Okay.
You do an introduction, and then you do a materials and methods. How you do calculations belongs in the method, not necessarily any one calculation. But how it would, like the algebra I just showed you, that paint screen, right? How I got to this equation would be in a method.
Okay.
Right? I didn't plug in any numbers here, but I told you how to get. That would go in a method.
All right.
And again, crystallography will do, and I'll explain everything you need for that. You only have to download the program. That's it. It's really, really small. It's a safe program to download. I've been using it for 97, so like 23 years now. So it works great. 97, 96, somewhere around 100. Right, so it works great. It's a little clunky because freeware, cheap. The only problem is if you own a Mac, because Macs and Apple in general have an issue of forcing you to update their operating system, which makes everything before that not. So for the crystallography lab, it's best to do it on. And if possible, you have an actual mouse pad. I know some of you, most of you, in fact, are probably using yours. But if you have a mouse laying around the house and an actual mouse plug-in and pad and everything, this crystallography exercise goes so much smoother with an actual than using a trackpad. Kimberly can tell you all about that. Right, but if there's no other questions, that's all I wanted to do today. Make sure you read the papers, and if you're assigned a certain paper, you guys know which one. I don't know the list. Make sure you know. We need to cover all 5 of them in my first or so, hour, something like that of lab next.
You said lab next time. Your mic
What's that?
your mic was cutting out a little bit. You said just the discussion next time.
Yeah, we'll do the discussion next time. I think we have a quiz too, right?
Yes, we do.
Okay, so the quiz will be on the enzyme kinetics stuff.
This one was over kinetics. The next one will be over inhibition.
Over what?
Inhibition.
Okay, right, the stuff we just did.
So next Monday we're not meeting here.
Next
right?
Monday is spring break, right?
Okay.
I think it is.
Can you guys post a list for the papers that we already signed up for?
I don't have that.
If you haven't. Never mind.
I
That
think it was
was
on the whiteboard at one point.
Yeah, you guys were supposed to keep up with that list, but you guys can always make a list in this channel as well.
Yeah, just put a list on here. Who's doing what? I don't care which one you do. There actually enough material in each paper that you can cover totally different things. So maybe make a list on here, something like this. Something like that. Right? That doesn't mean anything for any particular paper, but I'm going to cover these figures and do this paper. And you can make a list of what you want to do. That way we get everything covered. Right? And that's what you're going to explain to the rest of the class. And it doesn't have to say figure 2.
You can always discuss like a certain section of a paper or whatever you want to do.
But take a look at it over the next few days. You don't have to but something you and your group want to read the papers, of course. That's helped tremendously. But then explain it to the rest of the class.
And because there will be 2 weeks before our next meeting, would you mind summarizing everything we should have done by then?
Summarizing what?
Everything we should have done before our next meeting time.
As far as what to turn in, or
Like just a reminder about the papers, a reminder that we'll have a quiz.
yeah. So all of that's on the syllabus, but I'll put a note on D2L that says what you have coming up.
Keep in mind that your paper is not due until the day of the final exam. And
Please don't wait till the day before.
Yeah, please don't. And please email them to me. Dr. Meads has enough grading on his plate. So I'll grade them for him.
That's good news for you guys.
I mean, I'm technically supposed to grade them anyway, but...
I will put up an example of a paper so you guys can follow it as a template. Don't plagiarize it. And she will know because she'll see it too.
Plus, we might... Do you want to use my old paper? Whoa, what is happening?
What's that?
I said, do you want to use my paper? Do you want
If you want to put your paper up, yeah, that's perfectly fine.
Okay.
I was going to have to find one, but if you want to do that one, that's fine.
I still have mine. I wrote mine with you, so I think it's a good example.
Okay, any other questions? So, quick rundown of what we're doing over 2 weeks or so. Next week, spring break, we're going to cover the papers, we're going to take a quiz, and we'll do the crystallography exercise. So we can do that. And then the following week is the final.
Ooh, who's mine? Is that everything, Dr. Meads?
I think so.
All right. There are a couple of people asking about posting a video. Yes, I've taken several videos today. This might take me a while to figure out how to post the video, but I'll do my best. Does anyone have any other questions? Because I need to go. And Dr.
If we
Meads-
can
How are you gonna?
paper.
Whoa. Pardon?
Oh my gosh. I was gonna ask, how are you gonna grade the lab notebook?
I'm still trying to figure that out. I'll keep you updated on what I determine.
I would keep writing in your notebooks because they're going to be in the normal semester. I tell everyone that. And even more so for you guys, but obviously you're going to have access to them during the final. So write everything in your notebook.